Jin Seok, and I'm a PhD student at KAIST. Today, I will be talking about how to save the rocking drones presented by Yongdae's team in 2015. This is a joint work with Donggan, Junha, Juhan, Changwon, and Yongdae. Before we go into the details of my research, let me talk about drone system first. Drone is a sensing and actuation system, meaning that sense values are used to determine actuation through control algorithms. Let's take a look at the diagram below. The control system of drone is closed loop system. IMU, or inertial measurement unit, typically implemented as MEMS or microelectromechanical system, contains multiple sensors such as gyroscope and accelerometer. The physical quantities are measured from MEMS structure, which are digitized through AD sampling. Then the flight controller takes sensor values by using SPI or I-scale-C communication. After receiving sensor values from the sensor driver, the main loop determines the attitude and the position of drone, including speed of rotors. The rotation of motors change the physical states of drone, which are again measured by IMU sensor, forming closed loop. The drone is a safety critical system, meaning that any failure or malfunction can potentially lead to serious harm to people or property. Therefore, security and safety of drone is important, and anti-drone technology is getting attention globally. Among various anti-drone technologies, we visit the rocking drone research, which was done in our lab 8 years ago. Yunmok and friends have shown that sound can knock out the drones. Let's look at their demo. Playing sound in the right frequency causes resonation of gyroscope in IMU, which causes fluctuation of rotor speed, eventually crashing the drone to the ground. We run the rocking drone examples experiments on SITR software in the simulator. We inject sine wave to emulate the resonating gyroscope to the rotor control algorithm of our drone simulator. As you see, drone moves a little bit, but it does not crash as real drone example. Why was it crashing in the real drone, but not in the SITR simulation? This is the first question we try to answer in this paper. As performing real drone testing is too expensive, we developed acoustic injection testbed by modifying PX4, SITR, and HITR simulators. We try to understand the gap between hardware and software through this testbed. For simulations of gyroscope sensors, we had to develop dynamic modeling of resonating gyroscope sensors. Please refer to the paper for more details. SITR simulations do not involve any hardware operations and are useful for software-only testing. On the other hand, HITR simulations enable us to evaluate both hardware and software simultaneously. As shown in this figure diagram, our HITR testbed uses a simulator such as gazebo and pixel flight controller board to reflect empirical hardware operations. In addition to these simulations, we also conducted real drone tests to verify our implication analysis. These comprehensive approaches allowed us to truly test and analyze the security of our drone system. Now, let's look at the SITR and HITR simulate experiments. In case of SITR experiments, even with sound injection, the drone finished its mission. But in case of HITR experiments, similar to the original rocking drone experiments, the drone lost its control. The main difference between using SITR and HITR simulation is whether we use the control unit or the main board or not. Therefore, we conclude that some properties of control unit is not considered in SITR. What is this critical factor? Using the previous experiments, we analyzed the sensor data in frequency domain. The benign cases with the blue line shows the sensor data without sound injection. As you see, there is no significant resonation, having all values in low amplitude. After adding sound injection to SITR, the green graph resonation frequencies are sharply concentrated near 100 Hz. Note that this resonation can be easily removed if low-pass filter is applied. The orange graph shows very interesting HITR result. The resonation frequencies are spread over all frequencies after applying low-pass filter in the red graph. Some resonations still remain in low frequencies. Due to these unfiltered in-band noises, rocking drone was crashing to the ground. Then, what caused the spreading of the resonation frequencies in the orange graph? The major factor we found is a sampling jitter. The control unit releases IMU data periodically. However, our measurement indicates that this period is not accurate. Let's look at the graph. The blue dots are the sampling intervals in SITR. The green and red dots are the sampling intervals in HITR and with real drone respectively. The interval is not a near constant value. Sampling jitter exists because of hardware imperfections. However, the jitter is small enough to meet the real-time requirements of the drone control. In case of rocking drone, this sampling jitter is the major reason of crashing, in addition to the resonation of gyroscope. Now, let's look at the demo. In the SITR simulations, even after injection, drone hovers stably. The second is also SITR simulation, but with emulated the jitter value obtained from HITR. The drone fluctuates and eventually crashed to the ground. Now, real drone experiments. Note that in these experiments, we did not resonate gyroscope directly. We injected the resonation without jitter by modifying the timestamp of drone software. In case of real drone, without jitter, the drone does not crash. When resonation is injected using the original hardware timestamp, having jitter, again, drone crashes. Therefore, we conclude that the drone crashes not only because of the resonation of gyroscope, but also because of the jitter in sampling interval. Now let's change our gear to the think about the mitigation of rocking drone attack, particularly focusing on the recovery of IM sensors using unlocker. Before introducing the unlocker, let's review the existing defense mechanisms. A few possible mitigations were previously proposed. While mechanical shielding is the most effective approach, one has to be careful with heating problems. Some proposed to change parameters, but this may cause resonance in other frequencies. Sampling randomization will have the similar effect as the jitter in our paper. There are software-based solutions. Choi and Quinones proposed to detect attacks based on state estimations. However, they only proposed the detection without recovery. Choi proposed to recover gyroscope sensor values from accelerometer, but the recovery lasts only a few seconds. What is our main idea for signals recovery? As we discussed, the sampling jitter spreads the resonant signals, and the spread signals overlap with the original signal. The dispersed noise-like signals are hard to be eliminated by using conventional filters such as LPF or notch filter. But denoising autoencoder or DAE shows pretty good performance to remove noises in safety critical applications such as medical imaging, industrial process, and radar. This figure shows 2D DAE for image denoising. Our unlocker uses 1D CNN DAE. This slide explains how unlocker works. As other ML approaches, our solution is divided into training and inference. Our testbed, in other words, unlocker HITR, enables automatic dataset generation, which saves physical and temporal costs for collecting large dataset. We split the dataset into training and testing dataset. Using the training dataset, we train our DAE, which is used to generate the DAE inference model. Note that dataset and model generation is done at the server side. The inference is done at the just Nano or GPU single board computer for embedded device. We first test if DAE inference model works can remove in the testing dataset. We then test with real or any arbitrary data to see if it removes noises in various environments. In short, none of the testing dataset is overlapping with training dataset. Now let's look at the result. This is our recovery result using testing dataset generated from our unlocker testbed. The left and right graph shows the result for the accelerometer and gyroscope. The standard deviation of errors was significantly reduced from 56.264 to 0.296 for x-axis of accelerometer and 2.83 to 0.012 for x-axis of gyroscope. In the other words, the denoising works very well with the testing dataset. We also tested unlocker with domain adaptations. In other words, we tested with other dataset. The top three graphs on the left shows denoising result from real drone with software injected resonating gyroscope data. And the bottom left shows the denoising result from real drone with gyroscope resonated with speaker. The top two graphs on the right shows denoising result from different resonating frequencies, and the bottom right graph shows the denoising result with varying amplitude. We modified our testbed to generate this dataset. In summary, we show that rocking drone was crashed not only because of the resonation of the gyroscope, but also because of the sampling jitter. We also developed unrocker to remove resonating signals to recover the original signal. Finally, the unrocker code is open sourced. Thank you for your listening.
I'm just curious to know, do you expect other sensors other than the gyroscope, for example, to be affected by the same type of noise? And perhaps a converse question to that: do you expect other types of injection to affect the sensors? That this is coming from some papers that have shown, for example, that like you can aim a beam, a very focused beam of light, and Alexa, and get Alexa to do something funny with light instead of sounds. So would you expect that kind of stuff to affect drones and sensors and drones as well? That's right. I would help. So actually we tested also, actually the paper included several methods, and actually for that one speaker stuff is a very nice sticker, right? And I think that novel reality. So the only sound-based text are only the memories structure. So I think other sensors may be affected, but I mean that's okay. Nobody develops rushing drone as a technical solution because sound does not like that. We have a question from the audience here. Very nice talk. Given the insight that the sampling jitter substantially changed the way that the system reacted to your acoustic excitations, is there a way to change the acoustic excitations to either take advantage of that or to make it even more effective than just setting a simple direct tone? So you found that the sampling jitter made the system much more unstable. Is there anything that you then, an adversary, could do with the signal to make the signal itself have characteristics that would make it more malicious than the symbol tones that you used to cause it? And so the question is whether we can use that jitter as a means to attack workload, or change the signal to take advantage even more of the sampling jitter than you already do. So it's a good question, but I think we didn't think about it. Found that. Right. I don't think it's good, but I didn't think about it. And we'll know about it in NDSS by 2024.